Okay, so my clock now says it's 10 past 3. So here we go. Yeah, my talk is about DRBD9 and how we connect to OpenStack. Let me jump right into the topic with looking back for a few minutes. So this is an illustration that shows how DRBD8 works. And we will go through that so that you can easily follow me when we go to what is DRBD9 actually doing. So what we have been doing for the last 14 years is we built HA systems, and we really focused on the storage part of HA systems. So those two orange boxes illustrate the Linux kernel. And in that, we have a so-called I/O stack. That's this page cache file system DRBD thing. And we have a network stack. And in the I/O stack, we can insert certain things in certain places. And there where you see this DRBD box, this is exactly the same place where things like LVM hook in, where software aid goes in, and so on. So now DRBD mirrors all the writes it gets in, so it sends it over the network to the other node. Each and every write is written on the other node, and acknowledgement goes back. And only if we have both acknowledgers, that from the local disk and that from the remote side, we send it up to the application above us. So that's synchronous mirroring. We not only do that, we also do asynchronous mirroring. And that doesn't happen one after one request. In a real system, you have here hundreds or thousands of these operations going on at the same time, or 100,000. Okay, so the basic properties here. In case anything fails in such a cluster, and we are only concerned about things that fail and how we can recover from that. So if a node fails and comes back later on, DRBD will resync up all the writes that are missing on the previously failed node. It finds out that it has to do a resync. It finds about the direction, which blocks it needs to sync up. All that without that anybody has to care about it. We're quite proud about our performance. So this 160K ops we measured on the systems that was packed with reasonable SSDs and reasonable networking in between. You can't do that with your 1 gig link, right? Yeah, we do multiple volumes per resource. That means, well, that's better known as consistency groups. You need that when you have, an application like a database using 2 different types of storage. Imagine your database uses an SSDs where you put your logs, and you have RAID 5 where you put your table spaces. If you mirror such a setup, you want to mirror those 2 volumes as one logical group, because you cannot recover if replication fails for one of those 2. Yeah, we have pacemaker integration. We do that locally and over the WAN, even over the internet if you like. Yeah, and we're Linux upstream since 2009. It was released 2010. So this is the old stuff. If I want one thing, what you take from this presentation is DRBD9 has 4 new features. And if you really are eager to learn something, then try to remember the 4 features. Okay, we can now do 32 nodes, so we can copy your data 31 times if you like. I mean, who of you wants to have 32 copies of his block data? Right, me neither. Oh yeah, we have one gentleman. Perfect. Okay, The other important feature, auto-promote. I will come to that in a second. This is more like an agenda slide. Then we have this transport abstraction layer. That means we got our RDMA support. Very cool. I will come to that. And the fourth feature, DRBD9 I will also come to that. So 4. Just remember the number 4. OK, auto-promote. What's that? So for those of you who have already used DRBD, I'm assume that's not too many in this crowd. OK, it's a few. So before it was like on the left side of the slide. At first, you have to use an explicit command to promote the device on this node. And after that, you were able to use it. And after using it, you have to demote it before you can promote it somewhere else. Now, in DRBD9, we got this feature auto-promote. And that works that way. You open it for read-write access. And in the very moment, it promotes itself to primary. If you try that on the next node, you open it for read-write access. And boom, you get an error node back. Because it's already promoted. So I wonder why we didn't came up with that earlier. Yeah. The promotion process. Well, it's in milliseconds, whatever. It depends on 2 round trips. So it's basically a 2-phase commit. You have to execute over all the nodes. So if you have nice networking equipment, you will not notice it. Yeah, that was easy to explain. Now, the network abstraction. Yeah. So up to now, we had this TCP transport built right into DRBD. That meant we only were capable of using TCP to communicate between the 2 nodes. Now we abstracted it out. Now we have transport modules you can load on the fly. You can load 1 or multiple of those. And here we see the options. So with the TCP module, you usually use TCP software implemented in a Linux kernel on top of IP. And then you use Ethernet cards, which use an Ethernet switch, and so on. So everybody knows that. So then there is this RDMA side, the green stuff. That's the new one. And RDMA, that's interesting because it's really a new API, and that allows you to saturate pipes of 50 gigabits or even 100 gigabits. The old API, the TCP API, the problem lies in the API. So that's cool. We're really proud about it. Yeah, and the hardware you usually use are adapter cards from, well, which do either directly InfiniBand, or you can have this ROC key standard. So that means you have those new cards, this new API, and then you use switches you already know. Because nobody likes to learn about new InfiniBand switches, right? It took years until you understood VLANs and all that stuff. And suddenly, why should I use new switches? OK. Then also iWarp is an interesting option. Here on an iWarp card, you have a complete TCP stack on a network card, in the firmware on this card. So you get the new API, which is very performant, and you can run it over the internet, which means you need a 100 gig internet connection. Who has one? OK, somebody will. Yeah, so I think that's also easy to get. Then that was new feature number 3. Now we're coming to new feature number 4. That's DRBDManage. So so for the last 10 years, it was like that. DRBD is a driver that lives in a Linux kernel, and it is a virtual driver. So you need to configure it. You need to tell it what it should do. You need to tell it, OK, mirror this disk and use this IP address, and so on. So there's a small user space tool, DRBD setup. It has ugly long command lines. Nobody wants to use that. you give all the information on the command lines. Well, so that anybody can use it, we have this tool called DRBD9 that reads config files that are written in a declarative way. You copy this config file to all the nodes that are part of your setup, and then you use this command and get it configured. Now, OpenStack is about automation, right? So let's put some automation on top of that. Here it is. So DRBDManage is a daemon on top of that. It can spit out config files on your nodes. It can create the logic volumes where your data lives, which you replicate. It does that for you. And it has a dbus interface to a CLI tool. So pretty easy, right? What you need to use it is a few nodes with storage in a volume group. So this is your part, your preparation. And what you get out of it is you can request replicated resources by simply giving a name, a size, and a replica count. And it will take care of the rest. So it will find nodes where there's enough space. It will create the LV and will put the config files there, initialize DRBD metadata, and all that stuff. Okay, so here I have an illustration that shows the software architecture of DRBDManage. So we have the command line interface at the top. That's easy. You call that on the shell. That uses dbursts to connect to a locally running daemon. And that daemon writes things it think they're important to a control volume. So what is the control volume? That's a rather small volume DRBDManage will create on your nodes. It's about 4 megabytes in size. And when it writes there, it does an open. Open leads to an auto promote. So it gets primary. It can write the data, and when it's finished, it closes it again. It becomes secondary again. The other nodes have this DRBD event channel. So the daemon on the other nodes gets notified, oh, somebody else wrote to it. So maybe I read it. So this is a replicated database. Well, a very simple one. And DRBD9 itself is used to replicate this configuration and as communication channel at the same time. So this is this eat your own dog food strategy, right? Okay, so this illustration shows how you can imagine that with real volumes on real servers. So that should be 4 servers. On each you have this control volume. It's mirrored over all of them. And then you have user volumes. And usually, well, most of them are 2 ways redundant. You can have volumes that are 3 ways redundant, and so on. When you add a new node, you can do things like rebalance it, increase the replica count of D, and afterwards remove it from another node to create bigger chunks of free space. You can use the new space, and so on. One thing to mention here, unfortunately I don't have an animation for that. When you lose a node, when it goes down, DRBDManage does nothing because all the data is available. And it needs outside knowledge. Will this node ever come back, or is it gone forever? And in case it's gone forever, you simply tell it DRBDManage, remove node, rebalance. And that means that all the replicas that were lost are reallocated on the remaining nodes. But it cannot know by itself if the node will eventually come back or not. So this is outside information you need to provide. So it is a provisioning solution for DRBD. We have implemented that in Python. It manages LVs and so on. Yeah, it also does snapshotting for you, if you like. if you want that it can do snapshots, it will create all the LVs in thinly provisioned pools, so thin LV. Yeah, when you create snapshots, you can also give replica counts with the snapshot so that you don't lose the snapshot, blah, blah. Yeah, and right now we scale to 32 nodes, but we have it in the design, in the current code, that we will scale up to many more nodes. So how we will do that? We will add a concept we call satellite nodes. So simply speaking, you can have this replicated config database only on those 32, but those 32 themselves can manage more nodes. So on these satellite nodes, you will have only user data, not the control volume. And with that, we expect and we can scale like crazy. Yeah, but that's on the roadmap. OK, so far the foundation. Now, how hard is it to bring that to Cinder? I think not that hard. So we are at the OpenStack Summit. I'm not going to explain that, right? So we had this illustration of the control pane. So here the change is easy. You no longer use a command line client. It's connected by a Cinder driver. That means you create your volumes in the Horizon dashboard. You configure there a few pools like 2 ways mirrored, 3 ways mirrored, or things like 2 ways mirrored in my main data center with 1 offsite replica asynchronously on the other end of the world. And then the user just selects from the pool. And yeah, and we do an estimation of how much space is available in your pools. Think about that for a second. How exact that could be. Yeah, and then everything happens in the background. So you no longer need to fiddle with DRBD's config files or anything of that. Yeah. Nova, right. When you create Cinder volumes, you usually want to do something with that. So you usually want to attach that to virtual machines, right? So if the Nova, well, if you have a converged cluster where you use the same nodes for compute and storage, and our driver finds out of that Nova decided to start a virtual machine where we actually have a replica of the data, that's easy. The data is there. No iSCSI needed, no blah, blah, blah. In case Nova decides to start the VM on a machine where we do not have a replica, we can use the DRBD protocol itself for accessing the storage. Yeah? So you do not need to layer iSCSI on top of that. And that has a few little advantages, like when we have 2 nodes with storage, we can go to both to read the data, so read balancing. Well, when writing, we have to write to both, obviously. Yeah, so ideally, we want to make Nova a bit more clever to take hints from our system. We're not yet there, but this is an open source project, so eventually, in a few years. Or sooner if someone decides to help us. OK, so when you talk about storage in OpenStack, you always get different ideas, right? So some players think it's a good idea to put all the storage in expensive storage boxes. You connect to your compute nodes by a SAN that probably is not managed by any of the existing software drivers, which are part of Nova. So it looks something or similar to that. So where we are obviously going looks like that. So we want to use simply more boxes of the same kind with storage. And you have an Ethernet or the network of your choice, connecting your compute nodes and your storage nodes. And it's clear what the next step is. Just converge the thing. You know, use one kind of nodes, have local storage in those nodes, and have Nova and Zinder managing this set in an overlapping way. Yeah. Okay. Did I mention that DRBD is open source? Okay, so go get it. Try it out. DRBD9 is right now in its release candidate phase. So we have scheduled that the final release will happen in 5 weeks from now, so mid-June. The release candidates are in pretty good shape. You can get the source code from here. You can get access to RPM repositories if you shoot us a message. We are also a business, so you can get support from us, the usual open source business model. Yeah, any questions? Could you use the mic? Otherwise, I have to repeat the question.
So I have 2 questions. One is related to the largest capacity that you deployed.
It was a 50 terabyte volume. That was the largest single volume capacity. And to give more context, our code currently has a limit at 1 petabyte for a single volume.
Okay. In terms of upgrade, is it going to be a smooth cycle? How do you envision the upgrade from 8.3 to 9 version?
Sorry.
Like the upgrade cycle? Like, you know, when you have to upgrade, let's say you have version 8.3 now running? The upgrade. The upgrade.
Oh, the upgrade. Now I got it. Thank you. Yeah, the upgrade path is pretty smooth. The DRBD metadata on disk, that changed, and you can convert that. And the protocol, you know, if DRBD9 finds out, oh, the other guy is DRBD 8.4, it switches back to DRBD 8.4 mode on a protocol level. So you can actually do really a rolling upgrade. We are an HA. Our customers expect that from us.
Yes, I just want to make sure I understand something. So you can have, currently you can have 32 nodes in your cluster, and I would do LVM on these, and each volume that I create then can be, I can decide what my number of replicas is going to be, and then the system will distribute this itself.
Exactly.
Right.
Yes.
And each volume then can be, you said, can be 1 petabyte. So how would?
Yeah, I mean that's the limit. Each of those could be 1 petabyte.
Like A could be 1 petabyte. So that of course requires that on each system I at least have 1 petabyte LVM, right? Okay. just trying to make sure I mean, understand this.
That's our limit, yeah?
Yeah.
You know, you could deploy smaller nodes as well.
Right, but it's not like it would get striped across and I could like have a volume that's larger than one single node.
Yeah, now I understand where the question is going. No, we cannot stripe that out right now.
Right.
Sorry.
So my question is, well, if like your volumes look like Ceph pools and your replica sets, you know, I mean, it looks like this would compete with Ceph. Trying to understand if this, is that your point of view too, or?
I mean, you can put DRBD on anything that's a block device.
Right.
So if you like, you can put it on RBD, on Rados block devices.
No, I'm saying this would replace that, right? No? Is it competing technology?
Yes, you can. If you use Ceph to get block out of it, this is a perfect replacement. If you use Ceph to get object out of it,
well, their
this is not
object
any
is on top
replacement.
of their block anyway, so if they can do it, you can do it. You can put a Rados gateway on top of this, right? So, I mean...
Sure.
Okay, interesting, thanks.
Excuse me, one more thing.
Philipp, please use the mic.
So if block device A is 1 petabyte and block device E is 1 petabyte, you can have one virtual machine accessing, does it work? You can have one virtual machine accessing both of them, just like 2 hard disks, and then do LVM or something like that on top, so that you can do a 2 petabyte logical volume in the virtual machine, for example.
So, Philipp, I mean, in cloud we talk a lot about scale-out storage, and Ceph is a popular open source solution for that. If you compare your solution to, for example, Ceph, what would be the application scenarios where you say, well, scale-out is a better approach, and where would you say, well, this is the strengths where DRBD really shines, and where you would advise people to use such a more classical host-based mirroring technology?
I think Ceph shines when you need block storage, object storage, and maybe file storage from a single pool. I mean, that's really the awesome feature of Ceph. Where we really shine is if you have fast storage and you expect that after your software-defined storage layer, you still get performance. This is where this shines. So our whole data plane, that's in kernel. And we don't copy it around. If you use RDMA, we're really proud of the performance we get out of that. All our customers who drive the development of our technology ask for performance, and for performance.
Okay, thanks.
Yeah, please.
I have a question. So you just mentioned performance. Is there any performance number?
Performance numbers.
Yeah.
Yeah. So with RDMA, with an RDMA interconnect network, the best thing I saw was that we have a write throughput of a full all random write pattern, 4K, a throughput of 2.2 gigabytes per second. But that was a machine crazily loaded with SSDs, sorry, a pair of machines.
So this is a full SSD setup.
Yeah.
Okay, great. Thank you.
Yeah, I mean, when we have hard disks, the hard disks are so slow. Those numbers are boring, right?
With the converged model you talked about, compute and storage all in one box. So with what you've talked about, I can scale to 32 compute nodes with storage. So how do I mix your synchronous asynchronous model to go let's say to 250 compute nodes in the same converged model?
Yeah. Unfortunately, I don't have a slide on that. But just imagine you add here more and more nodes going beyond the 32 limit, and these additional nodes don't have a DRBD control volume, okay? And the whole setup works as long as one of your nodes that has a control volume survives. Only one is needed. So the idea is you have your many thousand nodes and put one node with control volume in each of those racks. And you need one of them to survive, and the whole system will survive. So this is the idea. Yeah, I really need to draw a picture of that. Okay.
I have a question.
Yeah, please.
So DRBD only provide the volume data replication, correct? So does it also provide volume management like snapshot or clone? As you just mentioned in the slide, it seems that it leveraged LVM to provide snapshots. Is it correct?
Yeah. So the answer is We use LVM to snapshot the volume, but the management of that, is in this DRBDManage thing in the daemon and database and so on. So you tell it, oh, I have a 3-ways replicated volume, create me a snapshot, and the snapshot has to exist on 2 volumes, 2 nodes, yeah. So it's managed in the system. So from the point of user, it is like, the whole system can do snapshots. And as with the volume, you can also say, give for the snapshot the replica count. In other words, how important is it?
Yeah, then how does it do volume clone? Just DD copy or can do anything clone? So how to clone a volume? Just the DD?
So how we clone a volume if we turn a snapshot into a volume again?
Yeah, or just clone a volume from a volume.
Yeah. So we use this thin LV on the nodes, thin LVM, and that does all the tricks on the nodes. So okay, so the straight answer is yes, it does that in an efficient way. We don't use DD for that.
Yeah.
All the magic is in thin LVM snapshots and our management on top of that, and DRBD is the replication part. Okay?
I'm back. So, what happens if you have, let's say, 1,000 VMs, a terabyte volume, and they all write? So, from the concurrency write perspective, did you test a large environment where you have lots of concurrent writes to ensure that you have no blocking, nothing with the scheduling, stuff like that?
Yeah. So if we have here many nodes and 1,000 volumes with 1,000 VMs, or even 2,000 volumes and 1,000 VMs consuming those 2,000 volumes, it's pretty distributed, A VM writing here in the whole data path, there is only communication between the node where you issue the write and your standby machine. Nobody else in the cluster is involved in the data path. So during I/O, there is very little contention. The only point where you have contention is when you do management commands. So I don't think we will be able to create, 20 volumes a second. I don't have numbers on that, but this is where the limits are, and I hope you can live with that.
Just wondering, in DRBD8, I had ended up briefly using the active mode with OCFS on top of that. Have you tested that on DRBD9? Does it work out well?
The dual primary, the active mode is still there. So far, we haven't worked on to scale that. So you can have only 2 primaries and 30 secondaries. So that is all still there. It is tested as we head to our release. So that's still there. But I think the dual primary mode, the active mode, has not that many use cases. I know people always ask for it. So what's your use case for using active mode?
What I actually ended up doing as a hack on top of things was key value store into a massive primary system. So. Oh,
wow, cool. A real use case. So usually people come up with things like, oh, I put cluster and LVM on top of it, and then I have logic volumes here and there. And that's actually stupid, because it's better to use to outsource all that into DRBDManage. But if you have a distributed key value store, dual primary mode is cool.
More primaries would be useful.
If we accept customers. Okay, do I have time left? 5 minutes. Okay, so if the questions are exhausted, well, I can actually fire up a few VMs and try it out. Didn't do a lot of testing on that, so please don't grill me if it fails. Okay, there's a terminal. Here's my mouse. Let's change the colors. Is it better? Yeah. Look at that. Okay, that will fire up 10 virtual machines on my laptop. You cannot see the CPU utilization thing that's on my side of the screen. The fan is coming up. Okay, the first one is running. Okay, so this is like the control node of my mini cluster. Okay, so we learned in the presentation that you need to have nodes with storage available in a volume group. So we're going to use this Scratch volume group, and let's go to a second node as well. Here's also the volume group. Okay. Then okay, that command starts a DRBDManage cluster. You issue the init on the first node of the cluster. That's it. Then okay, so what happened here? The add node command adds a second node to the DRBDManage cluster, and it happened that I have my SSH key active. So the program found out, oh, there is an SSH agent in the environment. Let's try to SSH to the joining node and to execute the necessary commands there. If that doesn't work, I can show you that as well, then you have to copy and paste this one command to the joining node. And after that, the node is joined. So node joining means it got the control volume and it got DRBD setup to mirror the control volume. So let's look at that. Yeah, so here's the control volume. That's the .drbd ctrl. And Status. And yeah, DRBD9 has a new status command. We no longer use proc DRBD. And that simply says, okay, here it is. I'm currently secondary. My local disk is up to date. I have one peer that's called V1, and it's also up to date. And I can then add more nodes, and then I would create volumes and so on. But apparently, now the break starts. So I can offer you, who is really interested to see the rest of the demo, that you join me outside and we continue it there. Okay, yeah, and we have shirts, so if you like this t-shirt, stop by here. We have a few of them. Thank you.